welcome to the AbsInt Videocast for the release 2010. My name is Christian Humbert and I'm going to present the latest changes in our binary level analyzers, StackAnalyzer, aiT Analyzer, TimeWeaver, TimingProfiler, and the ValueAnalyzer add-on today. Let's get started as usual with the latest updates in the graphical user interface. We finally introduced a separate file extension .APSet for the Workspace files. Remember, workspaces will reflect or will save the current state of an analysis project, including temporary files, results, the statistics, all the opened widgets. So let's have a look here in our favorite scenarios, a cube project. I'm going to open that one and perform, well, we have two WCT analysis and two stack usage analysis in this project for both the 1 and 10 millisecond tasks. And let me perform that in parallel here. You see, in the current state, I have here some error, here some loop bound issues, some warnings. Here's another problem. I don't get in worst case stack usage. The only completed analysis seems to be the 10 millisecond task here. Okay, now if I decide to stop working in this project today and would like to continue later, it would be a good idea to save a workspace file, right? And we can now do that here with save workspace, and this time from this release on we are going to save these workspace files in different file format or APSet. The format is the same, but the file extension has changed. In previous versions of the analyzer, we shared the APX between workspaces and projects, which was not the best idea, I would say. But this time we are changing it to APSet. And of course, it will be backwards compatible. So if you still have APX workspace files from previous versions, you will be able to open them in the new release, and the graphic user interface will recognize that this is a workspace and not a project file. So okay, let's save the APSet, and now you see in our directory I do not have any longer just the APX, but also the APSet workspace file. And well, I could here close the project or just load another one. And if I say I would like to resume the analysis state of that APSet workspace file, you can load that in our launcher. And you see it will directly open the analysis state as if we had performed the analysis right now. So especially we can double click here on the results and directly see the graph without the need to repeat the analysis. The statistics is also directly available, or also the temporary report files, for instance. So these are the new APSet workspace files. This update in the graphical user interface concerns the timing analysis only, the aiT and TimingProfiler especially. We have combined the pipeline and path analysis step in the tool chain, and this allows us to introduce a completely new and revised path analysis variant. You can see the effect here under setup timing analysis. We now have here on the path analysis variant 3 new modes. We have the auto mode, we have the basic block level mode, and the pipeline state level mode. The basic block level is in principle similar to the previous ILP based path analysis variant, and the pipeline state consolidates the prediction file based and prediction file based ILP. But now we are also introducing the auto mode, and this is quite convenient and nice for the user, since the analyzer now can automatically decide which path analysis variant is optimal for the task under analysis. And optimal here means with respect to the analysis precision and the analysis runtime and the used resources. Let's have a look back to our 10 millisecond task. We had this 309 microseconds as a predicted WCET for this task, and we were doing it with the auto mode. And if I go back now to the previous default, which was the ILP based, or in this case basic block level, you will see the effect if I redo the analysis. Just a second. Now you see it's 325.62 microseconds, so a slightly increase in the WCET prediction, since the ILP-based results are less precise in general. Now I'd like to introduce symbolic expected results to you and show how you can get editable columns in the overview. For that, let's perform these two stack analyses. All right, so well, in a 1 millisecond task we don't get a result for the user stack but for the CSA, and in a 10 millisecond task we get a nice final result of 128 bytes for the user stack and 320 bytes for the context safe area CSA. So remember, this is specific or special to the TriCore. All right, let's switch to this analysis number 4. And you remember that you can provide expected results here for the user stack and the CSA, and you had to do that for instance like this. You provide an interval of expected stack usage range. So in this case I know that we have for the 10 millisecond task a stack area allocated of size 256 bytes. And for the CSA, we had an area of 1 kilobyte basically. So, and if I redo the analysis here, you see everything is fine because the 128 bytes are lying in this range, or do not exceed 256, and the CSA as well. Yeah. With this release, we are introducing symbolic expected results because up to now you had to provide a constant upper bound here for the expected result. But many real-time operating systems offer allocated objects corresponding to a stack object or stack area. And in my example, I have a stack object which is called map stack task 10 millisecond. And you can now replace that constant value by the following expression. You can say, I'd like to refer to the width of this object, which is called map stack task 10 millisecond. Yeah? And instead of checking the result against a constant value or range here, I will now, or the analyzer will now extract the size of that object and will check the 128 bytes with it. So let's see how this works. Okay, so obviously we don't get an error. That means the stack is sufficiently high, or the stack object is sufficiently high in the size, but it's somehow suboptimal because we do not see any longer what is the actual width or size of that object. Even if we switch to the overview, we just see the result, which is 128, and we see that, well, our expected result is not exceeded in both cases for the user stack and the CSA stack, since it is green. But again, we have the symbolic reference here. Now, since we are able to edit the columns now in the overview, we can fix that. So we can click here with the right mouse click to the columns and say edit columns, and we can introduce some more interesting columns, like for instance the evaluated expected results. In this case, in this project, we are interested in the evaluated expected results for the user stack and the CSA. So I can just simply move that here to the right side, and if I click on OK, you see our column list has been extended, and now I also see the evaluated expression here of our expected result for both separated for the stack, the user stack, and the context safe area. Yeah? Okay, now just for your convenience, what happens if I change that to an stack object with a size that is too small. So for instance, if we change it here to the 1 millisecond task object, I know that this has just a size or width of 64 bytes, so obviously we will be exceeding it. So see what happens. Of course, we get the expected error message that the analyzed height of 128 bytes of the user stack does not satisfy the expected result of 64 bytes. And if we go back to the overview section, you see our expression or expected result field becomes red, and the evaluated expected result shows us why, because we have the 64 for that map stack object, and this is too small for the 128. Let's come to the next block on our feature list here. I'd like to show you the new unified and improved symbols and dwarf view, and the completely redesigned disassembly view. Let's start with the combined symbols view. If we go to information symbols, we do no longer have the dwarf view here as well, since these information have been consolidated and integrated into one view. You see above we have the dwarf debug information, or the type information coming from the dwarf debug info of the binary, and below we have this the symbols table. The idea to unify this is because if you are searching for some variable or some function, you typically do that in both views, in the dwarf, and if you don't find something in the dwarf debug view in the type information, you fall back to the symbols view usually. And now this will be done in one step. So let's come, for instance, to the 1 millisecond task. Let's have a look here to the graph, and for instance, if we have here some variable access, we could go to where is it? For instance, here where function pointer is called, and we could check where this load goes to with the interactive value analysis, for instance. For that, I should definitely start it interactively, of course, and let's come back to that point. Open that load instruction and say show value analysis results. And then we see that we are reading from a variable called registered message handlers. And as you know, you can, via the context menu, jump to that dwarf debug information. And now this is, of course, to be found in the symbols. If I do right mouse click and say find in symbols, you see what happens. It jumps to the symbols view and already filters the view for that address we are searching for, namely the registered message handlers. And we directly see that this is of type pointer to a list of struct st components, and also we see the information here in the symbol table completely aligned. All right, this is the new unified and improved symbols view. I think you will like it. So let's come back to the analysis graph to show you the redesigned disassembly view. You remember, if you would like to switch from graph view to the disassembly, you can click on the right mouse click and say show address and symbols view. And now you see we now have here a functions list on the left side, where you can immediately jump to the instructions of that function in the disassembly on the right side, so this is of course then filtered. If you say I'd like to see it completely, then let's start here with the 1 millisecond task. This is the entry function. You see the entire disassembly, and yeah, the design has been changed, so we now also show the address and the offset, the relative offset in by default in one line. You can follow, of course, jumps to that instruction, and yeah, there's also a possibility to display the opcode now here by some toolbar option. and of course the intermixed source code can also be displayed in the disassembly. Yeah, this function list can also be switched off if you like to have a better overview of this assembly. So this has been also redesigned and improved. For the last 2 points on our overview list here, I'd like to go to the 10 millisecond task WCT analysis again in our example and open the statistics. We show here a variable usage statistics, as you might know, that lists how often global variables are read and written on the worst case path that we have predicted with the WCT analysis. And up to this release, this list was restricted to global variables that are allocated to some section in the binary. We have extended that to also count access to variables which are not allocated, but where we have an entry in the symbols table of the analysis. So you will get now in general more information about variable accesses in this view. And the last point is about the analysis concurrency level. If you have access to a floating license with more than one token, you know that you are able to parallelize or perform the analysis concurrently also on one host machine. You can do that by clicking here on the fast forward button to play all, to perform all analysis, and you can use the slider to do it in a concurrent way. This is of course limited by the number of tokens you have available in the floating license. So if you do not want to allocate more than one token, of course you can start with just one. And as you can see, it starts with the very first analysis. But what happens if you realize that this analysis takes very long, since this has become a complex one, and if you know that no other colleague of yours is using the other tokens right now, now you can also change the concurrency level during runtime by clicking here on the progress slider and change the concurrence level again. So if you have four tokens, for instance, let's increase it, and you will see that now the remaining analysis of this project will also be started, since parallel execution is now allowed. And you see, since these are much easier to analyze, need less resources, they finish much earlier, while the other one is still running. All right, this concludes the overview of the latest changes in the graphical user interface. Let's move on. I'd like to show you an update on the hardware configuration view specific to the Infineon Aurix TriCore architecture. We also have done extensions on our ValueAnalyzer add-on, the interactive value analysis, but also for collecting initializations, which I'd like to show you. We have to discuss strong improvements on analyzing functions or tasks that have been written in C++ originally, especially with respect to the automatic resolution of C++ virtual member functions, now just based on the binary analysis. And last but not least, I'd like to present a new IS2 specification to allow preserving the abstract stack information over function calls. Let's get started. To see these new hardware configuration changes in the TriCore analyzers, you have to go to Setup, Hardware, and here you will find new edit boxes for the CSFR base address. We now automatically provide a value if the TriCore target has been selected and the corresponding core. So in case of core 0, if a task runs on core 0, then the corresponding CSFR base address will be that one. If we switch to core 1, you see the address change to 883, and on core 2 we start at 885 here. If the user can overwrite this value, of course, anytime, but if you omit that, this automatically derived base address will be taken. Next thing is the BTV address, the branch target vector address. If you provide that value for the BTV, which you can find in some initialization or startup code section by this instruction here. If you provide that address in combination with psw.is set to 1, then the syscalls, the traps of class 6 in the Infineon TriCore applications will automatically be resolved by calling the corresponding syscall handler, reachable via the BTV. So this can enable a more automatic resolution of the syscalls. If you leave it 0 here, then this means that you would switch to the interrupt stack when performing a trap, and then the recommendation is to not include the syscall handler within your task analysis and perform a separate analysis. Demonstrations of the new ValueAnalyzer features, I'd like to use the StackAnalyzer for ARM architecture and the scenarios example that has been slightly modified. We'll come to that point later. Okay, let's start with an interactive analysis of the 1 millisecond task. Remember, this is only possible if you have the ValueAnalyzer add-on licensed. Then we can go to the graph, and now the use case could be to search for write or read program locations of a certain global variable. In our case, I'd like to search for the global CAN-socket variable, and I just go to the symbols to search for the address of that one, and here it is. It's the address 2000 or 25460, and we can copy that address and go back to our graph, open the search window with Control F, and make sure to select here memory read or write, depending on what you would like to find. And in this case, I'd like to search for read locations of that variable starting at this address. And I found two precise accesses here. And the first one is here in the can receive data. If I double click to that, I open the function, and now previously I could go here to the context menu, say show value analysis results, to open the data flow information collected so far by the ValueAnalyzer. Now with this release, you can also do it directly from within the search or end result window. Now, if you click here, context menu, show in value analysis results, it directly jumps to the interactive presentation of the data flow values for that variable. The next new feature is an extension for the collecting of initializations feature, which we have presented already before. The original motivation is that we have an unresolved computed call in that 1 millisecond task, which is unresolved because of a global variable called register message handlers that is initialized in some separate init task function. And you can, with the help of the collect initialization, which is an inherent feature of the ValueAnalyzer add-on, you can collect that initialization of that global variable in a separate value analysis and then make the task analysis depending on that initializer. And so the computed call can be resolved. Now I have slightly modified this scenarios example in the following way. I'd like to show you by first doing an analysis here, and then we have we already see some small difference on the graph side. We have now a call of OS function, but let's come to the source code first. So let me fold that down. So that is the register message handler variable, which is later used in the 1 millisecond task to perform a computed call. And you see this has now been set by a variable called registered message handler init. And this init variable has been initialized with the address of a constant message handler table. So far so good. So it's just one more indirection than in the previous examples. But this time we have some low-level OS function call between these two variable assignments. And what then happens is, and we simulate in that US function call, that we lose the collected abstract memory information, so that afterwards we do not longer know what is the content of the register message handler in it. So I can show you that. So in the interactive analysis, let's go to our graph, and we have here the register message handler init, which is written probably at this place. We can check that with the value analyzer. Yes, so we write to our register message handler init the value of the message handler table, the start address of the message handler table. And this has been written to the address for the message handler init, which you can also see here in the memory cell content info. But unfortunately, this collected value, or this written value here, will get lost when we return from the OS function, because if we go inside of the OS function, there is some unknown memory access, and especially some unknown write access. So if I say here, show value analysis result, you see we write to an unknown memory cell, and that means we are losing or discarding any collected memory cell info so far, in especially also our content for the registered message handler init. You see it becomes unknown, and in the consequence, when we come back to the return address here and load the value from the registered message handler init again, it's unknown. And so in a consequence, also the store to the registered message handlers variable, the final one, will be unknown. Yeah? Okay, what you would like to do in this case is therefore making the init task function depending from itself while collecting the write to that register message handler init. So let me show you how to do that now with the iterative collect initialization. We just copy that name here, go to the AIS file, the local AIS file of this value analyzer, and we can say insert AIS annotation collect initialization for our register message handler init variable. That's the first step. So when we now redo the analysis, there will be a created dependency AIS file, and it says, okay, I'm collecting now with a strong and constant area contains annotation what would be the value for the registered message handlers in it. But now we have to tell the analysis as well that we are depending from ourselves, and this is by the new is induced by the new keyword called iterative collect initialization. Now, by this one, you see directly in effect, we have two rounds of the control flow and value analysis step, and now we use the collected information from the first round for the second round of this value analysis. Okay, and what we now have to do is just simply also connect the register message handlers variable. Yeah? So let's do that. we now just have to redo the analysis once, and let's check our dependency eyes file. And we see that now also for the final global variable, the register message handlers, this start address of the message handler table, which was written temporarily to the init variable, is contained and known here for the final variable as well. All right, now to fix the unresolved computed call, we just have to set a dependency to the initializer function, which itself is depending of itself, and redo the analysis, confirm that we can use the existing results, and you see the computed call will be resolved now. Now, before we come to the next section, I'd like to show you an alternative to the global collect initialization for global variables. We can also alternatively dump collected initial values at a certain program point. So for instance, we could go to the analyzer graph and say, yeah, for here after that call to the OS function, now we are not losing the value anymore since we have saved it in the collection. We could say, let me dump the data flow value for my register message handler here after it has been stored. For instance, at this program location, you can say copy eyes annotation, program point, and then let's go to the eyes annotation file, put it here, and instead of collecting that one, we just say dump, and for which variable we would like to dump the initial values. And if I redo the analysis, you see that it also writes the same content here, but this time we are dumping it at a certain location and not collecting it over the entire caller graph. For demonstrating how we have improved our static analyzer for the analysis of C++ code on binary level, I'd like to follow that small demonstrator program that has been initially provided by a customer of us. In this example, we have basically two tasks, a task T, which is an instance of a task template class, and a task F, that is an instance of a task fixed class. In both constructors, we are providing the gfunc, which is an instance of the C function class, as a parameter. And then in main, we call the run methods of both the task F fixed and the task template. Here is a declaration of both classes, the task template and the task fixed class. You see that we have this public method run, and we have this private method get value and a private member which is func, and this func is obviously copied during construction to this private member variable. And then when we analyze the run function, of course, you will see that inside of run, we are calling the get value in both cases, and get value itself, however, takes the func member and calls the get value method of this func member. And the interesting case now is, well, we see that in the analysis. If I run it, we get unresolved computed call warnings. And let's have a look to the graph. This is because inside of the get value function, so it doesn't matter in which instance we follow that, we are calling this func.getValue. And in previous release versions, the analyzer wasn't able to follow or to resolve this computed call, since this getValue method is a virtual function of that func class. We can see that in the information symbols. Let's follow the task fixed and the func member, and you see here it's of type iFunction, and this get value is virtual. So previously you had to create a separate C++ call target analyzer step, pass the source code, and then provide a dependency to the call target analyzer. Now, when using the latest release version 2010 of the analyzer, we can get rid of this extra C++ parsing step in the call target analysis. So let's remove that here. We also do not need the auto generation of the annotations and make it depending to the main task. Now the binary analyzer itself will be able to follow the vtable information in the binary and the dwarf debug information to resolve the computed calls due to virtual function calls. Let's see. Now the computed calls in both getValue instances will automatically be resolved for calling the C function getValue. This is because the func member, you remember, was of type at the end of the type C function class. And the C function class itself has, of course, an implementation of that getValue function. You see it here on this address. It's no longer relative to the vtable, it's an implementation address. And that's the only relevant implementation for getValue. So with these improvements, you will get much more computed calls resolved, especially when you use C++ code, without the need to separately analyze your source code with the virtual call target analyzer. Before I introduce the new aiT2 specification to preserve the abstract stack information, let me make an important announcement. With this release 2010, the first generation aiT specification language has officially been discontinued. That means the former aiT1 specifications will no longer be supported with 2010 and higher. If you still have aiT1 annotations in your projects, please convert them to the more efficient and modern aiT2 specifications. Of course, we also do offer some servers to help you with that conversion activities. Just let us know if you're interested in. Let me now introduce the new preserved stack annotation to you. For that, have a look to the first example. Assume we have a routine called foo, and this routine contains a call to routine bar. Assume further that this bar routine performs complex computations and at the end will have unknown or imprecise write access information causing in the analysis. Unfortunately, these unknown or imprecise write accesses will lead to a discard or destroying of all collected memory cells so far, including the local stack cell information of foo. That means when you return from that complex function bar, and when there was such an unknown memory and write access, then also the local variable information of foo has gone afterwards. Now with this annotation, the user can claim that the called routine bar, in this case, preserves at least the stack cells of foo. And this is not that unusual if bar, for instance, is just a void function that has no reference to any local variable of foo and isn't able to modify the contents of these local stack cells. In this case, the user can say routine foo calls to bar preserve stack, or even more generic, you can say routine foo preserve stack. That means that all calls inside of foo, even if there are more function calls, will preserving the stack area. And this will lead in general to more precise value analysis information. Let's have a look in a small example. For that, I'd like to resume that small example from the value analyzer section. Remember, that was our 1 millisecond task and our initializer. And when I run the 1 millisecond task, I have now an unresolved computed call in the 1 millisecond task can function. And despite we have the connection to the initializer, and this is because I have slightly modified the code, and I can show you that. So if we have a look to the source code here in the basic blocks, you see that I'm now saving the handler components, which at the end come from the message handler table, to a local function pointer variable, which is, in this case, placed on the local stack of our entry function task 1 millisecond can. Yeah? And then I'm calling a low-level OS function, which unfortunately performs a complex computation, leading to an unknown write access in the analysis, so that when we return from the OS function, the entire memory information, data flow information was lost, including the local stack cells of that 1 millisecond task entry function. So in more details, we have a look here to the machine instructions. So in this address here, when this load, we are loading the 4 handlers from the message handler table. So they start at these addresses. And then we are storing it onto the stack, the local stack of that entry function. Here we have an offset of 20 bytes to the current stack pointer. You see, we are saving it here to the stack area. And then we call OS function, and when we return from it, we are loading these 4 message handler start addresses again from the stack and storing it to R12, from which we are branching later, which is currently unresolved. So that means here when we load the stack cell, we unfortunately do not know any values anymore. But since this OS function is a standard void function and we do not provide any reference or pointer to any local variable, especially not our local FP variable, it is safe to provide the annotation we have learned. So let's do that. Let's go to the AIS file and say routine. Then we copy the name of our function here and say any call to the OS function shall preserve our stack area. So let's redo the analysis, and you see the computed call has now been resolved. And if we go to back to that program location, you see that when we return from the OS function and load from the stack cell, now we still know these 4 addresses for the message handler. And therefore the call can be resolved here at this program location. As usual, this was just a small selection of what has changed and has been improved in the newest release 2010. If you're interested in a complete list of release notes, please have a look to our website. So thank you very much for your interest. Take care and see you next time.